So we've now finished the topic on how speed cameras work. In this topic, you've learnt about waves, so you should now know what the terms wavelength, frequency, period and amplitude of a wave mean. You've also seen that the wave speed can be calculated using the wave speed is equal to the frequency times the wavelength. You've seen that we've got two types of waves, longitudinal waves such as sound waves where the particles making up the medium oscillate in a direction parallel to the direction the wave is travelling in, and transverse waves where the particles in the medium oscillate in the direction perpendicular to the direction the wave is travelling. You've been introduced to the concept that at boundaries a wave can either be transmitted or reflected. You've seen that if a wave is reflected from a boundary off a more dense medium, then it undergoes a phase change, whereas if it's reflected off a less dense medium, there is no phase change. We'll be investigating this in greater detail in the next topic, where we'll be considering how spectacles work, and we'll be looking at light waves, and we'll need to be able to work out whether they undergo a phase change when reflected off a boundary or not. We've also been introduced to the Doppler effect. So you know that a speed camera uses the Doppler effect to work out how fast a car is going. It can measure frequencies very accurately, so the small shift in frequency caused by the movement of the car tells the speed camera exactly how fast you're going.
Okay, so how our speed camera works is here it is on a pole. Now the speed camera is a source of electromagnetic radiation. So it's emitting waves here traveling out with the speed c, where c is the speed of light. These waves are reflected off a car. So here's a car traveling along the road away from the speed camera. So we know from our Doppler equation that the frequency detected by the car is equal to the frequency emitted by the speed camera over times c plus or minus the velocity of the observer over c minus or plus the velocity of the source. So we'll start by working out the frequency of the waves which are reflected off our car. Our car is our observer in this case, so this is equal to the frequency emitted by the source times c. Now this is the observer and it's moving away from the source, so we take the lower sign, so that's minus v. That v is how fast the car is traveling away from the speed camera, and the source, the speed camera itself, is not moving, so we've just got c. So this is equal to the frequency detected by the car, but the car now reflects this, so we've now got a reflected wave traveling back to the speed camera, which the speed camera is going to detect. So for the reflected wave, our car is the source, that's where the wave is coming from, and our speed camera is the observer. So in this case, we use the same equation again. F, we'll call it W dash. This is the frequency detected by the speed camera, is equal to the frequency emitted by the source, the car. And now in this case, the observer is stationary, so we've got nothing else after this C. The source is moving away from the speed camera, so we take the lower sign, which is the plus. Okay, so this is the frequency detected by the speed camera. So in this case, we know that f dash is equal to this, so we can write this as f c minus v over c. That's just replaced f dash with this expression over c, c plus v. We can see these cancel out and we end up with f is equal to c minus v over c plus v. Now the speed camera can physically measure the frequency of the signal that is reflected off the car. So it knows what f double dash is because it measures that. It knows what the frequency of the emitted signal was. It also knows what the speed of electromagnetic radiation is, c, the speed of light, and so the only unknown in this equation is the velocity of the car. So the speed camera can solve this equation to calculate the velocity of the car, and if the velocity of the car is greater than the speed limit, it will take a photograph.
After this, we had a look at relative motion. We saw how we could calculate the relative motion between two objects. We said that this led the ideas of relative motion and that all the laws of physics were the same in any inertial reference frame led Einstein on to develop their theories of special and general relativity. Finally, we had a brief look at how an ultrasound scanner works. You saw that an ultrasound scanner uses similar physics to a speed camera, except that it uses high-frequency sound waves rather than waves in the electromagnetic spectrum, radio waves, which the speed cameras use.